Hi, welcome to the presentation of the demonstration of my MSc thesis, titled A Comparative Study of Data Augmentation with Diffusion-Weighted MRI to Train CNNs for Prostate Cancer Classification. I was motivated to tackle this problem because, firstly, prostate cancer is a widespread disease which can be hard to image. Consequently, there's significant interest in machine learning to aid radiologists in this challenge. This aligns with my personal motivations. One, I've worked in prostate cancer before and I'm keen to further my knowledge about the domain. And secondly, I have a desire to develop my machine learning skills. Some background on the project. Multiparametric MRI is key in diagnosing prostate cancer. However, it can be quite difficult for radiologists to interpret these exams. Convolutional neural networks, which are a type of machine learning algorithms, are seen as one potential solution. However, they work best when trained on large data sets. This is problematic in this domain because the data sets of prostate MP MRI exams are typically very small, usually in the sort of range of a couple hundred patients. One way to get around this is to use data augmentation, which allows people to allows the algorithms to draw more information out of the sort of limited number of images. Fortunately, there's little research in what data augmentation strategies work best. To our knowledge, we've only found one study, which was led by Hayao, and what we attempt to do in our study is to reproduce their results using a different data set. We use the publicly available Prostate X data set. We also attempt to make our results more robust. So for each data augmentation strategy, we conduct multiple simulations using different random seeds. And this is important because convolutional neural networks have complex error surfaces with many local optima. So you can get different results if you use different random seeds. And we wanted to create a distribution of results. We focus on the DW MRI sequence, which is this one here, because it's generally considered the one which is the best sequence to characterize prostate cancer from. So here on the right, you can see the three images which are available in the Prostate X database for the DW MRI sequence. You have the ADC map, a combined B-values image, and the B0 image. So we took these three images, we took this particular slice, which was for the center of the lesion for each patient, and we basically trimmed it down to just focus on the lesion itself. So you basically end up with a 32 by 32 image for all three images. We then applied static augmentation. So this meant that we kept the original images, but we copied them, and then we applied various augmentation strategies. So we did rotations, you can see here, we did shears, we did translations, and we did scales. For our model, we used the cross-entropy loss, but we also added an L2 regularizer because some academic literature suggests that this leads to better results. For the optimizer, we used stochastic gradient descent, but we also used momentum, yet again because academic literature suggests that this leads to faster conversion. We used a shallow convolutional neural network just because we felt we could get better results based on the literature, and two, it would lead to faster training. So we used five convolutional layers, 2 max pooling layers, and a couple of dense layers at the end. The key tools used in this project, all the coding was done in Jupyter notebooks. We used Python, and specifically we used the machine learning library of PyTorch to build the model and also do the data augmentation. In terms of hardware, we used a NVIDIA GeForce GPU running on CUDA. For our results, we got fairly promising results. So going into the study, based on the other similar study, we thought rotations would be best. It actually was the only one where we couldn't generate significant results. So you can see here that the orange band is the 95% confidence interval for our baseline results. So that's the models trained on non-augmented data. And you can see the rotation results. And this is also the blue band is the 95% confidence interval for the augmented data. You can see the bands never actually move apart. So effectively, we never didn't make any better models using rotations. But you can see actually here we did create worse models with a 90% rotation and a 180-degree rotation. With translations, we achieved our first significant result, which was the 2x2 translation. Yet again, not particularly promising. With shears and scales, we started to see better results. So the shears, you can see we started getting quite a bit higher. So the best mean one was a 45-degree shear, clockwise shear, I believe. And that was an AU-RSC of 0.67. I should mention that the way we evaluated our models was using the area under the receiver operating characteristic curve, which is a very common way to measure the effectiveness of binary classifiers. Sorry, I should have mentioned that earlier. With scales, we got our best results. So you can see with a 0.4 scale through to a 0.2 scale, we got very, very good results, which were clearly significantly better than the baseline. This was quite surprising to us. We weren't expecting to see these results. We then took our best individual models and our best baseline models. So we took our best, our best individual model used 1.8 scaling, and our second best had a 1.4 scaling, and our best baseline had achieved a 0.7 AU-RSC. And we tested these on the holdout set, which you can do for Prostate X. You can see, I mean, really promising, you can see that we got pretty similar results to what we did on the validation set, which leads us to believe that our results are fairly robust. And also we achieved fairly good results. Overall, we achieved a 0.76 with the 1.4 scaling, which was exactly the same as what we achieved in the result on the validation set. So if you compare this to the actual Prostate X challenge, we would have been the 19th best model with our 1.4x scaling, and our baseline would have been about the 39th best model. Some key conclusions. I think the first key conclusion is we can see that data augmentation clearly improves the accuracy of our convolutional neural nets to classify prostate, DW, MRI exams. This is obviously what we're expecting to see. One of the other things we saw was we can make it worse as well. So there were results, to go back to rotations, you can see we created models which were just clearly worse than the baseline. So it is possible to be over aggressive in your data augmentation and basically make the models close to unusable. The thing which we found quite surprising is we were expecting rotations to be the best data augmentation strategy, and obviously from our results they clearly were not. So this kind of lends to the belief that it's difficult, potentially impossible, to manually design the optimal data augmentation approach, which is typically what research groups do. So in reality, reading through the literature, there are probably better ways of doing this, in particular using some sort of algorithmic approach to find the best data augmentation strategy. A good example of one of these approaches is something called Auto-Augment, which was generated by Kubik, a researcher called Kubik, working at Google Brain. Thank you very much.